So one of the two algorithms that we will consider for constructing minimum spanning trees is Prim's algorithm. Okay, so Prim's algorithm takes a graph as input, made up of vertices and edges with weights, and returns a minimum spanning tree. And again, that is a tree that connects every vertex in the graph, but without any cycles. And so you can see that update, that initialization, that first for loop looks a lot like Dijkstra's. In essence, it sets all the costs to infinity and sets all the previous's to nil. In this case, that's the same thing as setting it to -1, and allows you to pick any node. We will use vertex A as the starting point just to be consistent, and so we set the cost of that vertex to 0, and then we add everything to a priority queue. As you see there, it's a min priority queue, and while that queue is not empty, we will remove the minimum item and we will make an update if we can add that vertex to the minimum spanning tree at a lesser cost than it has previously been part of the tree through. So what we mean there is that unlike Dijkstra, this is not an accumulated cost. This is just a cost of the edge between the node called V in this case, the vertex called V, and its other endpoint, which is called Z. And so if Z can either become part of the tree through V, or if its cost can be reduced by connecting to the tree through V, then we make that update. And then this last statement, which says decrease key, that basically means since we've made an update to Z, we have to reorder the priority queue so that the lowest value is at the top. Let's walk through an example of Prim's algorithm. Okay, so we have set up a table that is very similar to the one we use for Dijkstra, and we've got the graph that is shown above, and we will begin at vertex A, and that's just an arbitrary decision. The idea is that we eventually want all of the vertices to be highlighted as being part of the minimum spanning tree. Okay, so initially the minimum span set is empty. There is no minimum span set, but we have set the cost of A to 0 and the cost of all remaining vertices to infinity. And so we can now place A into the minimum spanning set. Okay, so A is in the set now. And we will now look at the things that are adjacent to A and improve those costs, those infinity costs, improve the costs of connecting to those vertices through A. So you notice that I can connect B to this tree at a cost of 5. Well, B has a cost of infinity right now, right? So that's something that we want to do. Same thing with C and same thing with D. So let's walk through that. Okay, so cost of 5 connected to A for vertex B. Okay, so we'll highlight that particular edge. A cost of 6 through vertex A for vertex C. So this is akin to adding those particular nodes to the minimum spanning set. We haven't formally added them yet, but we're improving the cost of adding them. Let's look at D. I can get there at a cost of 4, so I can attach D to A at a cost of 4, and that's better than infinity. And A is not connected to E or F at all, and so those remain at infinity. And this iteration of the loop is complete. And we will now do, just like in Dijkstra, we will now look at our minimum value because it's a min priority queue, and we will pull out vertex D as the next vertex to add to the minimum spanning set. Okay, so we add D then, and now our set looks like this. And again, we would like, we want all of the vertices to eventually be bolded, meaning that they're part of the minimum spanning set. As we look at D, we now have to ask questions about, can we improve some of these other existing potential connections, and can we bring new things like F, for instance? Can we bring new vertices into the set? So let's evaluate D. So from D, I can connect vertex B at a cost of only 2 versus the cost of 5. Okay, so I'm going to make that update, get rid of that, and fill it in with this. Okay, and then from D, I can also improve the situation at 6, cost of 2. Previously, it was a cost of 6. So now that D is part of the tree, the minimum spanning set, I can add other nodes through that connect through D. Okay, so we'll swap that out. And D can also improve F's condition. Okay, F was previously at infinity, and we can now connect F to this whole tree at a cost of 4. And so we do that, and evaluating everything else, that remains at nil, and then A and D have already been removed, and so those are no longer in the queue, so they're not processed. And so this is where we are after this step. Okay, now we've got a tie between B and C. They're both at 2, so we're going to take the one that's earlier in the alphabet, so we will DQ B, and we will see whether we can improve anything. Well, right now, C is being connected to the tree by D at a cost of 2. Now that B is part of the group, I can connect to C at a cost of 1. So we'll remove that one and replace it with that edge. Okay, and looking at the other ones, there are no changes. Okay, B can't get to E, and B can't do any better in connecting D. Well, D is already gone. It's already been processed. Okay, so now as we look at this, we have C and we have D. I'm sorry, we have C, and that is our next one that we will pull off. Okay, so we pull off C, and we evaluate the other nodes. So C is now in the set. So we have to evaluate E and F because A, D, and B are already removed. So we just evaluate E and F to see whether the situation could be improved there through C. And we notice that previously at E we had infinity, a cost of infinity, but now we can add this to the minimum spanning tree through this vertex at a cost of 5. And so we will do that. Okay, and then also we previously were adding F through D at a cost of 4. Well, we can add F now through C at a cost of 3. And so we will do that. Okay, and we'll make those 2 updates, and this iteration is over. E and F are now in the tree, and the the lesser is F, so we pick off F. Okay, and we're going to evaluate whether, so F is now part of the group, and we're going to evaluate whether we can improve E at all. Well, F can connect E at a cost of 4, whereas E previously was being connected at a cost of 5 through C. So we'll make that change. And now we're pretty much down to one vertex, and it's just a formality. We remove it, we make that last vertex part of the minimum spanning set, and the algorithm terminates. Okay, so let's take a look at the cost, which you see down here at the bottom. The cost for this particular, the minimum spanning tree cost for this particular graph will always be 14. There may be cases when you have different combinations of edges that are in the minimum spanning set, but the cost will never be below 14, and that's simply the 4 plus the 3 plus this 1 plus the 2 plus the 4 here. Okay, so if we add all that up, we get 14, and that is the minimum spanning tree cost. And this is a minimum spanning tree algorithm, and it's yielded that cost as well as the edges that make up that minimum spanning tree. That's Prim's algorithm.